Good morning, good afternoon, good evening, depending where you are. It is my great pleasure to present the next talk in the series of the distinguished lecture series of the IEEE CEDA, the virtual lectures. So today it is the pleasure of having Dr. Rajiv Joshi from IBM TJ Watson Research Lab. He's a very well-known and well-achieved member of the community. So he doesn't need any introduction, but just to do my job, I'm giving a brief introduction and his biography. He is a research staff member and key technical lead at TJ Watson Research Center, IBM. He received his BTech in IIT Bombay, India, master's from MIT, and Dr. Ing from Columbia University. So his work on the interconnect process and structures has been used from sub 0.5 micrometer to all the way down to 5 nanometer technology nodes. He had also worked a lot on the yield analysis and yield prediction. He has also worked on various memory technologies and all various from SRAM, DRAM, TRAM, and MRAM technologies. He received 4 outstanding technical achievements, 3 highest corporate patent portfolio awards, and large number of patents, over 250 US and 400 international patents. He has several publications and has many invited and keynote talks in various conferences and firms. So he received IEEE Daniel Nobel Award in 2018. He's the Best Editor Award from IEEE VLSI in 2015. So he is inducted in New Jersey Inventor Hall of Fame in 2014. And he is a recipient of 2013 IEEE CAS Industrial Pioneer Award and Mehboob Khan Award for Semiconductor Research Corporation. He had several Best Paper Awards in various conferences. He was also a distinguished lecturer for IEEE CAS and EDS societies, and he's now a distinguished lecturer by IEEE CEDA. He had several other awards that basically you can, it's a list keep going and going. So I do not want to take too much time from his lecture that you're all waiting to hear, and I leave the floor to him for his very interesting talk on predictive analytics in machine learning for VLSI circuits. So Rajiv, please. I believe you're muted.
Can you hear me?
Yes.
Okay. So thank you, Mehdi, for that elaborate introduction. And greetings to everyone from Rajiv Joshi. That's me, and I would be giving you overview of predictive analytics in machine learning for VLSI circuit. This work, our work as well as external work, spans over last 15, 16 years. So I would like to acknowledge first, CEDA Executive Committee for the DL Talk support, and especially Mehdi, who encouraged me to give this talk, and also Professor Vaida Kanj, with whom I have been working while she was at IBM. So why prediction or predictive technologies or methodologies are key? Because it can do a lot of things for humanity. This is the computer that you see. It is a supercomputer called Summit IBM came with, and it had 30,000, close to 30,000 GPUs and 10,000, processors, CPUs. And it has all these machine learning techniques which can predict all these interesting things. It has predicted 77 compounds against coronavirus. So you can see the power of prediction, right? So you can develop these techniques, machine learning techniques or predictive techniques, to utilize for humanity as well. So outline of my talk basically is semiconductor trends. I will give you areas of growth, challenge of cost, yield, and power. Now, re-emergence of AI and ML techniques, thereby utilizing some of these techniques, predictive analytics, and the applications, especially to VLSI circuits, logic, memory, advanced technology, reliability, and some of the novel techniques which have been developed based on that, and we have contributed to the literature in this era, and also future opportunities. So let's look at the semiconductor growth trend, right? What is there for EDA? So if you look at that, the semiconductor industry, the semiconductor growth is definitely, is growing. And you can clearly see that in 2021, I mean, there was a little bit setback last year because of the pandemic, but nevertheless, the chip demand keeps on growing. And then there is a electronics design automation part to it, and which is, you can see the CAGR, or the compound annual growth rate, is 6.5% from 2017. And most of the work, looks like going in the system on chips as well as automotive sector, as can be highlighted. Okay, so 2024, this industry will grow to 14 billion. Now, what is growing actually in this field, right? So you can see there are ups and downs. Here is the year-on-year growth rate. Some is positive, some is negative, but ultimately it keeps on growing. And AI, machine learning, 5G, IoT, cloud, all these are the buzzwords. Not only the buzzwords, but these are the ways of future. And the market growth that you are seeing, in this area, I want to point out that the memory side, especially the memory side, you can see 96 billion in 2016 to 2022 is 100, and now in 2022 will be 150 billion. So memories are forever. I mean, that's famous songs by memories are for forever. I think this is the way to go, in my opinion. And since the memory is getting consumed, the need to optimize or develop the memories is quite critical. So what happens then? Look, I mean, all these memories are formed of devices, right? So there is always process, voltage, temperature variation. But the challenge is, how do you understand it? How do you capture it? Okay. And then there are many parameters which go and affect it. But the key one is VT, or the threshold voltage, which affects many aspects of this. And if you look at the roadmap sort of the devices, and this is from Samsung, you can see from planar FET, then we had this SOI in between, then FinFET, then gate all around. FinFET had only on the 3 sides. Now it is all over, gate all over, all around, and then the nanosheet. So this is sort of the scheme it looks like. And then the question is, how do we manipulate this variability, or understand it, or optimize it? That's the key interesting aspect of it. And can we utilize these machine learning techniques and make it in a very useful for giving feedback to the device technology? So what is happening is, continuously the problem is the yield is decreasing. Okay. And the yield and the cost is ramping up quite a bit. Okay, and you can see these charts. I don't have to go through in detail, but because of the time limit, but you can see that the semi-manufacturing yield and the technology node in nanometers, you can see that the yield is going down, okay, here. So you have to do a lot, and the number of logic steps, which is this red line, shows that everything is getting very complex. So how do you manipulate all these things? And that is where, if we can throw some techniques, predict some capabilities to understand, to optimize the yield, to make it better, that is where the name of the game is. So why AI and ML soaring now, right? I mean, so we have seen that data, is growing. Then there is there are a lot of algorithmic developments, and the compute power has increased. So this feedback loop, growing data, increasing compute power, everything is in our favor. And now we can solve complex problems in AI or machine learning. And all these things are so critical. And that is why AI or ML, AI started in 1942, 1943 timeframe. And Alan Turing, you must have heard, I mean, he's a famous scientist, has done very, I mean, he's the one who started in those days. And you can see now revisiting of this work is really taking shape. So artificial intelligence and the machine learning, they go they go hand in hand. But artificial intelligence, as you can see, the machine learning has all these learning techniques, supervised, unsupervised, reinforcement, and then you can name many of these things. But artificial intelligence gives you additional flavor to it, and that is the reasoning part of it, natural language processing, and the planning part of it. And some of the best machine learning algorithms that you have seen, or you might have used it, and everybody uses it. We have used it since our graduate days, undergraduate days. Many of these evolved over time. And linear regression, logistic regression, decision trees, naive Bayes, probabilistic theories, artificial neural networks, which are now becoming popular, and k-means clustering, for the failure mechanism, anomaly detection, Gaussian mixture models, principal component analysis, nearest neighbors, support vector mesh, and then you name it, okay? And some of these things I will cover in my talk as I go along, how it was done, from the yield perspective, and that is the idea behind, behind this or the motivation behind this talk. So, predictive analytics for nanotechnology, right? So, accurate yield analysis in nanometer scale design is very critical. And complex materials, atomic dimensions result in manufacturing variations along neighboring transistors in logic and memory. Now, here I'm going to talk about SRAM. But by the way, I can bring in the other topic, which is a separate topic of discussion, which is a non-volatile memory. This is a volatile memory. But in non-volatile, you can do similar things. However, the parameter of optimizations just are different. Okay. So just keep that in mind, but similar techniques can be extended, can be applied to non-volatile as well. Okay. And they will come in very handy in some of the topics that you must have heard, or they are emerging, is compute in memory, and using the fancy emerging devices or memories like RERAM, FERAM, all kinds of PCMs, MRAMs, and things like that. So anyway, again, you need analysis, yield prediction, even if you want to take that to a production level. So achieving high yield requires detailed analysis, accuracy in modeling at tails of variability distribution, because the memories are not one. Okay, it's many in megabytes kind of thing. So exploring scales of statistical variability distribution for accurate yield estimate is computationally very expensive. So then for the big data, you have all these multidimensionality, right? I mean, it is not one parameter. There are many parameters, VT, L, W, mobility, you know, you name it, all kinds of things, grain sizes, how they affect, many things like that. So exploring the performance enhancement for the code and compare the techniques for the regression methodologies and possibility for cloud-based deployment, because these days all the work can be accessible or done very effectively through cloud, and because many applications can be developed there and then can be just accessed on the local machine. So now another motivation is the cost per transistor, which I mentioned is rising, and manufacturing yield is critical, right? So this is the cost which is shown here for transistor is rising. So now what are the techniques, the yield analysis techniques that we are talking about, right? The predictive techniques. So of course, Monte Carlo is a very famous technique which has been used for ages, and people still keep on using it, for many reasons. However, when you bring that technique into reality or try to apply it, then you can see that Monte Carlo, spends too much time in the passing region, and it becomes extremely slow. We want to go in the tail region of that Gaussian distribution, and it is very difficult to achieve that. So then there are other techniques people have used, and which are called as the sensitivity analysis or directional methods, right? And the directional methods are basically, you have these variables VTN2 and VTN1, and then you try to dive into in unidirection, but that becomes extremely pessimistic and it loses accuracy. So remember, two things we need to achieve. One is the accurate prediction, and the second one is the runtime or the simulation time. And they do not go hand in hand for these techniques. So then there is a grid-based methodology where you form smaller grids for sampling between the two. And these smaller grids, you take only the grid points and then do the sampling along that line. So that kind of sampling, these kind of sampling techniques result in non-accuracy or inaccuracies. And they're also very slow. So then there are a lot of techniques which can be developed and which can be mastered, in this regime, in this analysis, I would say. And there are MC method, which is Monte Carlo, simple Monte Carlo method, variance reduction method. Then I mentioned about the directional or sensitivity analysis technique. Then stratified sampling, which is based on the uniform groups and uniform weightages. Then Latin hypercube sampling, which is, you equally divide your samples, variables in equal samples, and you form rows and columns, and you select only from those columns and rows, okay, one at a time. And then the sequential Monte Carlo methods. And then I will talk about importance sampling and mixture importance sampling. That is sort of the basis when we started doing the work, and which is, and I will explain why those methods proved better over the period of time that we have exercised. And then there are geometric approximation, boundary methods. You will find all these in the literatures. And then there is another class which is very interesting and important one, is the surrogate models. And the surrogate models are nothing but sort of a behavioral models or sort of approximate model, because you do not have the exact model. So what you do, you just approximate it through some polynomial fitting or responses, some neural networks, support vector machine kind of thing, where you can figure out where the failures are, passings are, and all those things. The Gaussian-based method and high sigma Monte Carlo methods, where you play with the number of samples, passing region, failing region, similar to what we have proposed. So to give you in a nutshell, in a summary, what happens, Monte Carlo is that this is a Gaussian distribution, as you can see, and the Gaussian distribution, and we are interested in the higher sigma region because we want to find out, if there is one failure or two failures in a cell, then even if you have redundancy, you cannot overcome other failures that those are seen in the you cannot correct it. So it's better to predict it or make your memory robust in such a way that you can dive down to a very, very low high sigma region or very, very low failure probability region. So what we do, as I said, Monte Carlo spend a lot of time in the passing region, but it doesn't go in this rare failure event, which is the tail regions, right? So what we came out with first is a combination of uniform sampling. And so what we do first is use the uniform sampling for all the variables, understand the failure, that is, find out the center of gravity of failure using uniform sampling, then move your distribution. Okay, this distribution is moved from origin with a mean that is x minus mu s, and it will give you and shift it and start sampling in this region. And sampling region then automatically will give you near the failure region or a rare failure region, I would say, where the failure probabilities are extremely low. And that is the key point I'm trying to emphasize here. And there is a lot of maths and the code and all that. And the paper, the first paper was published, Roida Kanj and myself, and Sunny, around 2006. So just to give you an idea, I mentioned there are two important things, okay? Accuracy and the speed. So how do we do that? Now, if you look at the speed, the speed, this is the speed here as a function of sigma value. And you can clearly see that the speed up for this mixture importance sampling can be increased dramatically. And this table is the, gives you the result. So here is the Monte Carlo samples, here mixture importance sampling samples, and here is the speed up. And you can see the sigmas given here, and the speed up using the mixture importance sampling is around, of the order of 5, and Monte Carlo samples needed are 10 to the 9. It's a large number of samples are needed, while mixture importance sampling needs only, small amount of samples as we go along, because we are sampling in that failure region, shifted distribution, and we are closer to the failure region, where the probability is the lowest. So that is the idea behind using this method. So it gives you speed, it gives you also accuracy as well. So if you, for the big data and the yield prediction kind of thing, you need to develop all these test structures for process variations, build the statistical transistor models, all these things, and simulate macro using step 2 here, that is all these transistors. And so the flow becomes like chip design, macro simulation, usage of parametric mean and sigma variation in step 2, pruning the variables through sensitivity analysis, then because you don't want to have large data, large, I would say, large number of variables, you can prune them through the sensitivity analysis, then use the predictive analytics using pruned variable failure analysis, and then do the design optimization, and then go back and fix the design process and optimize it. And along this line, the program or the code will give you which are the sensitive transistors which can be fixed or which can be analyzed. So I would like to dive into application to the memory, and I'm going to be a little fast because I need to cover many slides here. So I have to be a little fast along this line. So bottom line is, if you are talking about, say, SRAM in this case, so SRAM is a 6 transistor cell per se, and you want to read 0 from this SRAM. So what happens is this cell supply is at, say, VCS. Assume that in this case, both VCS and VDD word line are same, and you want to read 0. So while reading, what happens is there are other cells on this bit line. This is called vertical is a bit line, and those are turned off. Only one line is selected, word line, but there is a capacitance on that bit line. So the charge could be dumped into that 0. So if the charge increases significantly, then that 0 can be flipped during reading, which is a failure. So you have to set up the failure criteria like that. And for the writing for the 6 transistor cell, you have to make sure that 0 becomes 1 during writing. If it doesn't, then the writing or the writability, there is a failure. So these are the kind of criteria that you have to set up in order to run these techniques. So if you do that, and if you look at various scenarios, for example, word line sitting at VDD and the cell supply is sitting at VCS separate there, and you have a cell supply at VCS and the word line is at VCS, then that is, it's like a, or you can boost the word line also, or boost the cell also. Boost meaning dynamically you can boost it. I will not go in the details of that. You can read the papers. But boosting meaning dynamically you can jack up the cell voltages or word line voltages. So in short, what I'm saying is you can decouple the supply voltage from the word line to the cell, or you can have same supply word line as well as cell, and see what happens. And then you want to understand how this design would change in your system or in your analysis. So if you look at when you analyze it through this mixture importance sampling technique that I described, and if you plot VCS versus VDD, you'll get all these regions, okay, passing regions, and this is the passing region, and all these they're marked based on the sigma values. Higher the sigma, higher is the robustness, okay? And you can see that at higher sigmas, the region for word line connected to VDD while cell is connected to VCS has a very narrow region, while both of them are connected to VCS, word line as well as cell. You can get a much broader range of operation. This has a much larger sigma value. So this is what happens. So this technique is very useful in determining what type of things that you get, or what type of design, you can discriminate the design actually, which is better, which is good or worse, or things like that, and optimize accordingly. So what are the things in the predictive capabilities that has been demonstrated? So it has a high accuracy. We can go up to 9 sigma or even beyond. There should not be a limit based on the this has been worked many years at IBM. And we also commercialize this. So it has a high capacity verified over 20K plus variables through external client. And there are internal techniques that have been developed as well beyond that, and many other usefulness. And if you look at the application of this, it goes beyond limit. You can see this has been applied to memories, EDRAM, FIR filters, analog, techniques, and many other things were done. And this is the hardware corroboration. You can see model versus hardware on the right-hand side, and they can match very nicely. So that is the way of corroboration of model versus hardware. So there are other memory applications where we can look into the EDRAM, for example. I will not go talk about the circuits here, but there are sense-amps, primary sense-amps, secondary sense-amps. And you can see that if you plot using the mixture importance sampling, the sigma value as a function of read bit line discharge, then for the two operations, read 0 and read 1, you get a very opposite trend. And then it defines you, it gives you an idea about the working technology, or I mean the working, I would say, the range, or the technology range, or the process range, or things like that. So another application for this is the local evaluation circuitry. So apart from the memory, we have taken it to the local circuitry or local or peripheral logic, although it is not as many as the memory, but especially the sense-amps or the local evaluation circuitry is the key. And here we are trying to evaluate in this local bit circuitry, local bit select circuitry, what type of topology of the transistors is critical or not critical. And you can see here clearly in these diagrams that if you have normalized yield as a function of VDD, you have a, either you can use cross-coupled PFETs to reduce noise on these bit lines, or you can use cross-coupled NFETs, PFET or NFET, which is better? How do we know? This is the answer from this figure, okay? That cross-coupled PFETs show, this is the dark blue, is lower yield versus cross-coupled NFETs at strong P, weak N corner. So you can choose now topology which is suited for your circuitry using these predictive methodologies. Okay, so this application is to the hit logic. So I will talk about from the mixture importance sampling perspective. If you look at, if you plot something where you need to latch, the data you need to latch, and what is plotted here in this chart is the data and the restore signal, okay? The data, the restore falling edge delay as a function of restore signal falling edge delay. So what does that mean? Well, when the data falls, the restore signal should come later than the data falls, not earlier, right? Otherwise, the data will be corrupted. So we want below this line, 45-degree line, all the points should be below this. However, we saw points above this line, and that is because this was done through the Monte Carlo analysis first, using 10K samples, and it was very difficult to predict, to find out. Then we used mixture importance sampling, and you could see the trend that we observed. And this was done at 0.7 volt, and this point that you see here is the mixture importance sampling at 0.7 volt. And it showed that the yield indeed dipped because of the timing issue. So this were the timing issue problem that was observed. So this is how mixture importance sampling came in very handy. Accuracy as well as speed came really played well. So so what happens is the another thing that we wanted to look at is the taking the looking at the impact and then integrating using the TCAD. The TCAD is the really difficult, but it is before the technology. The TCAD is predicting before the technology matures or even the technology starts. So the TCAD uses fundamental equations of physics and try to give you some basic idea about the technology, the variations, and all kinds of good things. And we made an attempt to do so. And so here is a classic example where we did device level understanding about using Monte Carlo, that how the LER, that is line edge roughness, metal grain granularity, random dopant fluctuation affect the pull down device, the pass gate device, and pull up device of SRAM. And you can see what the dominant factors that we noticed, and so the RDF as well as the MGG, that is metal grain granularity, because the work function these days have been set up by the metal gates. Okay, so in that there is there are variations of the grains, and this is what we observed, and we utilize that information as we moved forward. Also, the capacitance prediction was done because in order to predict capacitances of a SRAM cell, okay, the combination of word line, that is the interaction of the word line to the bit lines and the power supplies, the rails, all kinds of things was achieved using some of these some nice techniques, the 3D work that was developed, and using that we were able to predict capacitances. And this shows a 3D graph, 3D picture, where we could figure out the interactions. And why is that important? Because you need the variation, variability understanding, accurate RC extraction understanding, and then the modeling, that is the mixture importance sampling or whatever technique that you want to use to simulate your circuit. So this is what the methodology we came out with, which is called as fast and accurate TFM flow for SRAM, which is nothing but the TCAD for manufacturing, where we use early technology input, physics-based model, 3D to 2D, then the 3D TCAD for capacitance extraction, which I mentioned, then inputting the transistors in the TCAD itself using the IBM local TCAD setup, and then we implemented in the mixed mode fashion using large number of transistors, this mixture importance sampling technique with the capacitance information, variability information, and we could predict the yield, just like you predict through SPICE analysis. This was done through the TCAD. Okay, now Monte Carlo would take 6 months to do this kind of a thing, 6 or 7 months, while this technique that we came out would do it within a day, less than a day. Okay, so this was the power of this methodology. And then we predicted yield for 14 nanometer for different cells topology. And to the amazement, I would say that whatever we predicted, for example, capacitances or the variability information, we were less than 5% off, less than 5%. And it was really amazing piece of work that was done. So application to reliability, I'm going to go through this very fast because I do not have much time. And again, the idea here is when we talk about reliability, we'll talk about end of life and the beginning of life. And there are many factors which drive this this analysis in that direction. So aging is a universal rule. I mean, we always know that, right? Everybody ages, including devices. Okay. And the memories, especially in the unreliable world, SRAM comprises 50%. And then that's why we need to take extra precaution. And what happens is the lifetime is limited by NBTI, PBTI effects, and other reliability considerations. And threshold voltages, and over the time they increase. And there are other mechanisms which play a role in the yield degradation. So again, I'm not going to go in the detail of this. This is the negative bias temperature instability. Here, what happens is when you apply negative bias, and especially accelerated fashion like temperature or time, then the voltage, the threshold voltage of a device, especially PFET, increases, as a function of time. That's bottom line. And then there are mechanisms like channel hot carrier. Then there are impurities, the defects, which can break down and help this mechanism further aggravated that. And then there will be also time-dependent breakdown as well. So all these things play a significant role. And how do you predict that? So So what one can do is that there is a lot of earlier work which was done, and that is, that as a function of time, as I mentioned, the VT increases if you apply stress to it. But then when you remove the stress, it recovers, right? But not to the fullest, but it will try to recover. So how do you do that? So there are some techniques which have been proposed earlier in the literature, and that is, do not keep the memory stationary. That is, what it means is, if the memory is sitting there, if it is holding 0 or 1, whatever data, then you need to toggle it at certain point. So one of the techniques was just to use data from the memory and then invert it and write it back in the opposite fashion, so that the memory gets toggled, so it is not sitting there for a long time, and thereby you are relieving the stress, or you're not putting it under stress for a long time. So that is the idea behind this. Now, if we can predict it, first of all, then I think that would be better. So these are hardware techniques which are used, right? So the idea is to propose, a technique, and again, extend our mixture importance sampling in this domain. So how did we do that? We utilized dual power supply technique, exploit redundancy repair to improve yield, and find the best repair assignment at beginning of life. And pure hardware-based search methodology is very expensive. So we propose the methodology also, which will help us to reduce the hardware testing time using this method. So the idea is to use the dual supply, which I mentioned, for the cell as well as to the periphery, or cell word line as well as to the periphery, and separating out, you can do quite a lot of things, to the life of that device. So dual supply, as I mentioned, this is the word line. This could be VDD, VCS, as mentioned here, and the bit lines could be at different plane. And we did a lot of work on that aspect for, and many of these techniques, came into manufacturing and also offered in many industries. Many IP industries also offer dual, supplies, VCS and VDD. Okay, so there, by playing with this, you can generate different, you plot VCS as a function of VDD, and you can get different probabilities. And for cell, in order to improve stability, especially for 6 transistor cell, VCS plane is higher than the VDD plane. So for large arrays, we know that there are redundancies are involved, right? But estimating probability versus VDD, find Vmin such that the number of fails is smaller than the redundancy quota. Otherwise, you cannot use redundancy because you will run out of redundancy. So this is what this graph shows you. So always remember that redundancy will be, and you cannot afford to have a lot of redundancy because the size will increase. So it's better to have a good technique to repair right from the beginning. And this is what, is very critical. That is, in the beginning of life, a repair corner is used, okay? Multiple candidates exist at T0. T0 meaning is the beginning of life, and end of life. We add all these variabilities, including the NBTI, PBTI, whatever variabilities are there. And then we use that, and we again improve using the T0, we try to improve the yield at EOL. And sometimes we may dive into also some of the repair or redundancies, which will be useful. Remember, normally redundancies are used for defects, hard defects, but we can use very sparingly if need be, even at the end of life situation. So now, as I mentioned earlier, there is a hardware-based approach, which is very, very exhaustive. Meaning, if you get a chip back, you want to look at the end of life, and in order to do that, you have to do a lot of experiments. So the lot of time is wasted. If you go through this flow, you'll understand it, that you have to test fresh part and remove any defective part, then stress the part at high temperature. And if the if you remove the stress, if it doesn't pass, then you go back and define a new corner. Okay, so this is a very elaborate process on the hardware when you are testing it. Then if you use this method, elegant method, where you choose, perform statistical analysis simulation to predict with the repair corners, and then choose the T0 best condition, then T0 best part to remove and repair at that level, then stress the part at high temperature and all that. And if those parts don't pass, then go back. And this is done through the software, this feedback loop, everything. So you are not wasting time. Once you understand this, once you get this, then you will figure it out, what is the important factor here, how you have saved time, the test time on the hardware. So you give that feedback to the hardware testing, okay? And this will improve the hardware productivity. So I'm just going to move a little fast and give you that what did we do to confidently say that we made the chips and everything worked beautifully. So there was a hardware corroboration. This is a 45 nanometer. And subsequently also, we did this, that I don't have the figure to show, but just trust me that it was done that way. And so 45 nanometer SRAM hardware corroboration. So hundreds of chips were measured. And what you see here is the VCS and VDD. Okay, so this is the best, okay? The blue line, the blue contour that you see are the best yield, and the gradation is goes from best to worst, okay? That is VCS as a function of VDD, and these are the contours that represent the statistical method that I described to you. this is how we generated these contours of sigma values. And using those contours, we were able to match. Now these dots that you see were the actual measurements. And indeed, those dots mapped very well in those regions for that VCS VDD combination. So that was the real success, saying that indeed the methodology as well as the hardware, the corroboration with the end of life with repair prediction was really successful. That was the idea behind this. So now I would like to talk to you about more about the. So I talked about basically taking the transistor and using the mixture importance sampling and using the SPICE model and all those great things. Now, I mean, I mentioned that it increases the runtime compared to Monte Carlo by 5 orders of magnitude. The question is, can we do even better? And I highlighted that before, that can we use surrogate methodology, right? The surrogate meaning sort of behavioral models or some kind of approximate models. Can we do that? And the answer, this is where we tried to answer that question. And this is where we try to predict based on some of the machine learning techniques using this. And you can see that first example was the application of sparse regression. That is, instead of using SPICE for importance sampling, or the second step, we wanted to use a classifier or a good model, I would say, a good surrogate model. And you can see the first stage, generate uniform distribution, identify the failure points, calculate the mean by considering the failure points, find the cog, that is center of gravity minus mu. This is done through the standard SPICE simulations using uniform sampling. The uniform sampling is very fast, very quick. Then what do? Well, in the second stage, we generate an approximate model or model based on the first stage. And that is the sparse regression, or using the sparse regression, and based on this uniform sampling, we generated the model and then subjected it to the importance sampling. Okay, so the sparse regression comes with its own own things, pros and cons, and so the methodology was it's a k-fold validation. In this case, 5-fold cross-validation was used, and divide the data set into mutually exclusive training and test data sets. For a given fixed number of significant variables, regression terms, find average test set of errors, and using these, dark, the rectangles that you see, use that data for training, and light color for, cross-training, validation kind of thing. So also increase lambda. Lambda is in the equation, that is the number of terms in the model, and repeat the step. And so choose the model with the lowest average cross-validation error. So that is the purpose of this. So what happens is, when you do this kind of analysis, so you have false prediction, okay? The false prediction is composed of false passes and false fails, okay? False passes and false fails. So once you have that model developed, you predict and plot as a function of this threshold here. The threshold is plotted here, okay? And when you predict, then you plot, you can see that false fails decrease as a function of that threshold here, and false passes increase. And this is the total prediction, right? Total, this gray line. So which is the range where we should work? So this particular region here, where is a flat or the minimal kind of failures that you see is the region where we try to target and use it. And first we determine that threshold by plotting these two and getting a region, and use it, and then use the threshold to predict the mixture importance sampling, the second pass-fail criteria, which gives us reasonably good accuracy. Okay, well, you need reasonable good accuracy, but also the speed increases by an order of magnitude compared to standard, compared to the mixture importance sampling that I described earlier. So there are advantages of these sort of behavioral or sort of model kind of approaches. And that is reflected here in this chart, that you can, if you plot the yield as a function of number of simulations, if you use the second order terms in the sparse regression, then you can see the deviation here at different voltages. While if you use larger terms, then you can go much, much higher. So what is the advantage of this technique? Well, we were able to do a lot of variables, more than, 10,000 kind of variables using this kind of methodology. Of course, there are cons as well, and the cons is, selecting these orders and all that, it becomes and then iteration process is also an issue. So then we have this application of logistic regression, similar concept that I described in the sparse regression, but instead of using sparse regression, we use logistic regression. And logistic regression is a popular machine learning algorithm borrowed from statistics, and build a model to describe the relation between a categorical outcome. It is mostly probabilistic. It is a binary. You can have 0 or 1, the results. And you'll see that in the terms of function here, that the data is categorical, and it follows a relationship, P y is equal to 1, that is probability y is equal to 1, with x parameterized through this theta. Okay, and y is equal to 0, it is this, and then the function is defined like this. It is a sigmoid function, that is 0, it goes from 0 to 1, so it saturates at 1. And then, if the h theta is above 0.5, then it is 1. So it is like a binary classification here. Okay, so with this kind of a technique, comprehensive and computationally efficient SRAM cell analysis methodology, we propose the logistic regression with order feature selection for fast and accurate mixture importance sampling. So bottom line is we're trying to bring the second step into this model, okay? And that's the key idea. And the idea also is to increase the speed even further, so that we can have larger circuits, complicated circuits can be utilized with this. And this is nothing but a flow chart. And I have described this in words, that is, you generate uniform sampling, simulate the circuit, and using the uniform sampling, you generate the failure regions with mu and sigma, then build the logistic regression model using that, using regularization and cross-validation, and obtain the theta, those coefficients, the theta that I showed you earlier, and use that closed loop kind of model, and use and shift the distribution. I mean, shift your model distribution inside using mu x and sigma x, and predict the outcome, that is, predict the yield. So once again, much, much faster and reasonably accurate. And you can see here that the failure, the critical features for this minimum error as a function of experiments and false predict just keep on reducing, and they are very small number, and it's like a less than, I would say, 2% kind of thing, less than 2%. And you can see that here also on the right hand side, the phase 2 important sampling points prediction, and they look pretty good, as a function of voltages and extreme low voltages and things like that. So this is the kind of thing that we are talking about, of employing these machine learning techniques and making the speed up as well as maintaining accuracy. And very interesting ideas are still there, which are being employed. And then there is an imbalance in real data set, because the real data sets are imbalanced and are dominated by a group of normal sample points existing along with a small group of minority abnormal sample points. And what happens is, if you have a large number of passing regions versus small number of failing regions, and we are trying to fit the data, then the model becomes really unrealistic. So that's why this is an imbalance in the data. So there are various ways of doing that, and that is what is called as data balancing technique. Data balancing technique is nothing but you can account for the minority, or I would say minority oversampling technique. Okay, so if you have minority points, failing points, which are showed in the blue, you can correspondingly increase those, oversample it, giving certain rules. Okay, and this technique is a synthetic minority oversampling technique, which is used. And if you use that technique along with mixture importance sampling, you can see and get the model out of it and fit it. Then the original versus SMOT technique, you can see the improvement, significant improvement in that. So we try to encompass wide variety of techniques with what we earlier proposed as over these years, and try to enhance the literature in that direction, so that we could exploit the machine learning techniques in that domain. So here is another one which is from IBM, and this is called as enhanced machine learning model for adaptive Monte Carlo analysis. So what you do is basically initial support vector classifier or regressor, where you collect pass-fail training data using uniform sampling, again the same thing, and you assign scores to it, pass or fail scores, and then you plot it. So original samples in this region, and this is the the variable 2, variable 1, and then these are failure points, and then you draw these boundaries, decision boundaries here. And the maximum margin is, in the original samples. Then you try to prune it, okay? That some of these, you focus on this region and try to prune this. That is enhancement samples, collect pass-fail training data that is predicted to lie near the street. This is called as a street. And then define another boundary, which is a new decision boundary, and utilize that for Monte Carlo analysis. Okay, small set of samples. And this support vector system kind of technique machine technique is very useful in that direction. And you can see the number of counts as a function of classification score here without enhancement. That is, this is without enhancement. It's much larger, failure misprediction. While if you use this prune or enhanced sampling here, then you can get very less amount of sample using the support vector machines. And then you can go through this table and you can see that false negative predictions are much smaller, while you can maintain the accuracy, things like that. So indeed, some of these techniques are utilized very nicely, and it gives us, it allows us flexibility to predict the yield, optimize the devices, and optimize the circuits, and bring to another level of simplicity. So predictive analytic techniques and its impact and utility used in IBM chip design phase, fully validated. Thousands of Power 7 chips use this as I mentioned, used in Summit, which used Power 9, and many other many other machines. It is used. So it is not just a technique that we disclosed, but we also developed sort of a interest in the universities, and we work with the university folks and colleagues to evaluate and work with them in this direction. So finally, summarizing my talk, semiconductors are approaching atomic and economic limits. Variations are greater at atomic scale, so yields are lower, and design is more challenging, needing more sophisticated tools and computation power. And predictive analytic techniques are a fundamental part of chip design and becoming increasingly important. So this has been used in IBM, and enhancement for high dimensionality and usage for big data analysis is demonstrated. And future opportunities are abound. And I can tell you that this talk was just focused on VLSI circuit side, but there are a lot of opportunities or applications outside of semiconductor, such as finance, data and trend analysis, medical applications, farming, and many other things. And people are already exploiting this, okay? But if you can come up with new ideas and new techniques in this domain, there are always opportunities. Perfectly adaptable as a cloud computing service if security risks can be alleviated, and further opportunities abound throughout EDA for cloud computing services in the fabless semiconductor industry. So the opportunities do continue, and I'm sure there will be many more to come. Once again, thank you very much for your attention, and thank you very much for giving me the opportunity as a DL speaker to speak at the CEDA seminar. Thank you.
Thank you very much, Rajiv, for the very interesting and intriguing presentation, which was very comprehensive and covering very aspects. So we have time for a few questions. You can simply write your questions in the Q&A section, and we'll see how we can handle them. Or you can raise your hand, and then I will give you the option to talk. So basically, whatever that you prefer, you can either write your questions in the Q&A, or you can basically raise your hand and I give you the option to talk. Sumant, you can unmute yourself and talk. I mean, I give you.
Sorry about that. Hello, Dr. Rajiv Joshi. Thank you so much for your talk. It was a great presentation. So my question is on while we kind of talked about like machine learning, usage of machine learning techniques for the design of the memory, are there like, what do you think of leveraging these machine learning techniques and verification of the memories, of speeding up of the verification of the memories? Thank you.
Yeah, so, okay, so verification, right? I mean, a very interesting question. However, remember, if you can define in the verification, right, suppose, I mean, I'm just throwing some ideas here. I never tried that, but you have all these multiple patterns, say, and you are trying to employ and use that in that direction, and you want to see how much coverage in that memory could be done or could be achieved. That is the only way I can think about it. But there are means, you know, in order to in the memory section, there are ways of verifying the memory, right? I mean, you know that. I mean, these are, you know, developing these patterns or generating the patterns or full coverage, you know, to that extent. And also the ABIST, right? I mean, we use the ABIST array. This is from the hardware side, but you know, so there are various methods. So to me, I have not thought about this particular, you know, there could be a possibility, but I don't know how to, you know, bring out in terms of these, you know, at least I have not thought about it
Okay.
at this point.
Yeah, thanks for the answer. Yeah.
There are also a couple of questions on the Q&A. I can read them, and it would be great if you can quickly or briefly answer them. So from Hussam Amrouj, so any special challenge that was not known and at sub 7 nanometer become a serious challenge?
Sorry, the question is there any challenge or no challenge below 7 nanometer? Is that the question?
I think it means that, is there anything that is, you know, a new set of challenges that come from 7 nanometers? So I can let.
Right. So, I mean,
I can elaborate maybe very quickly. Thanks for the talk, first of all. So all the techniques that you showed dealing with those, let's say, traditional problems since 45 and those problems getting larger, is there any new problem now even will start to challenge the techniques and the methods that we used to use for the older technology? So something like quite a new due to, I don't know, 5 nanometers and really these extreme feature sizes where even our existing methods becomes or start to struggle to deal with those challenges?
Well, as you know, right? I mean, when you go down, right, the roadmap is, say, nanosheet, okay, and then there are stack devices. So, what are the interaction between the neighboring devices, the stacking point of view? Will there be an issue? So, as far as the parametric side, these parameters still will remain the same. I don't see any newer thing in there, right? I mean, you have all these VTL, W mobility, all these things are there. I mean, these are the basic physics. But other than that, you know, if there are neighboring effects or other, you know, stress effects in the, you know, those kind of things can be an issue or possibility. And especially the trend that people are pursuing in future is also going, you know, exploring different temperature regimes. Okay. And in that aspect, do we see anything new in that? I do not foresee significant, but there could be some new elements as well. That's all I can tell you at this point, because the newer technology are a little you know, beyond where we have not yet started playing with these variability things. Variability comes into, I would say, yield stuff, because it comes to comes into play only when you have a notion or vision that it is going to get there in production, or there is a feasibility sort of, right? So far we have not dealt with that yet, but maybe in future. So so it is really hard to predict at this point, but I don't see significant phenomena in that direction. apart from what I just mentioned, like neighboring or stacking effects that would play a role, because there will be stacking devices if we ever use that technology, right? And gate all around is on the way. I mean, it will be there. So that's all I can say.
Okay, thanks. And about the inherent randomness that could come at such devices from quantum physics, could that be a big problem? Because then the same device, and you repeat the measurement, or will start to, I mean, at 3 nanometer or 5 nanometer, quantum physics becomes so dominant. How we can see it as an additional source of variability? And could those methods deal with that?
You see, all these methods are probabilistic methods, right? I mean, if you look at many of these, apart from, I mean, they are sort of derivatives of Monte Carlo. And right? I mean, the probabilities, anything, we can do, all these principles are hinged on that. I mean, it's all probability. The thing that we cannot predict, precisely in a closed loop fashion becomes probabilistic. And the quantum effects and whatever you're telling, yes, I mean, these methods, I'm very confident that this can be really exploited very well to a great extent, because if we believe Monte Carlo or probabilistic methods, then these methods will give us some guidance to a good extent, I guess. There is no doubt in my mind.
Okay, thanks. Yeah, sounds good.
The other question is, can you talk a little bit about AI applications in digital ASIC designs? What are the current trends?
Okay, so the question is, what are the applications for AI applications in ASIC?
AI applications in digital ASIC designs.
Right. So I think one of the major, as I said, if you look at, I mean, where do we use these, okay, so the AI is a very broad term in this case, right? One of the things that, again, we are not, I mean, I'm not working on that. I mean, this CAD for AI CAD is getting also very popular. That's where you can bring in some automation and some kind of a relevance that is using the prior data, using the prior models. How can you do the synthesis, place and route, all kinds of things like that. So that is where I think there is a need to do that intelligently using that prior learning. Okay, and my colleagues are working on, some of them are working in that direction. And so you'll find applications like that. But one of the major applications of this sort of these machine learning kind of approaches were so adaptable in the memory side very quickly because there was so much need. But now the automation part or the intelligent part is also playing a significant role in that area. Provided if you have a lot of, I mean, there are many things you can do actually when you have a lot of data, prior data, and you want to predict in future little intelligently, okay? And also reutilize it intelligently, whatever was there. And yes, so you'll find those AI applications in the, I would say, CAD AI in the, for synthesis, for, these place and route, or which, for reducing or reducing timing delays. All these things are very crucial, and some of my colleagues are playing with that.
Thank you. And probably the last question is, could you give us the future direction of ML-based predictive analysis in technology library characterization?
Okay, so I mean, already it has been used, you know. I mean, there is nothing that I can say. I mean, a lot of these techniques are used in the ASIC standard cell characterization. When we were working on this mixture importance sampling, we were doing that in the standard cells that we had. We were characterizing the yields and the delays and optimizing them, all kinds of things. So it will be used, still used, you know, in future. There is no doubt in my mind that anything to do with automation, I think there is no doubt that those techniques need to be used to improve human productivity, period. And some of these techniques are exactly doing that for benefiting, or at least telling us, you know, when there is so much variation across, you know, we even cannot predict, or we have to rely on the foundries, then we need to understand whatever we design really makes sense or not. And that's exactly these techniques will be useful for, even for these ML techniques, which will be, I mean, you know that there are companies which are, which have these products, okay? And I will not go in the details of those companies, but you know that. And those companies are doing, you know, these machine learning techniques for the yield predictions and characterizing and all those things. So to answer your question, we will continue to use these ML techniques for standard cell delays, especially, and for the latches, you know, the timing of the latches, the writability of the latches, all kinds of things in that direction.
Okay. Thank you very much. Thanks for taking time to answer all these questions with details and with patience. I would like to also thank all the attendees for attending these presentations. As you know, all these presentations are recorded and it would be posted on the CEDA website and the YouTube channel. Also stay tuned for our next presentations. The next one in the line is on in-memory computing, which will be presented by Sharon Hu, and it is scheduled on August 19, same time. So see you next month, and thank you, Rajiv, and all the attendees.